In this session we continue on with a discussion of the phenomenon of tunneling, and you probably remember from near the end of the previous session that tunneling is what happens when you have a free wave come in from the left, hits a barrier, let's say of a potential barrier, say of height V0. Let's assume that the energy of your incoming free wave E is less than V0. Okay, so instead of just going over it in a sense, it penetrates it to some extent. We've done that from the previous analysis when the width here was effectively infinite. You get this exponential drop off, dropping to zero. But in this special case, when the width of the barrier, this I don't know, call it a hill, is fairly thin, then it's what you just see here visually. You can see that the exponential drop off, it's occurring. But let's say the barrier, the width, little a here. So the barrier starts at, this is the x-axis here, talking one dimensions, is at 0, and so the barrier stops at x equals a, positive little a, and from then on, so from a onwards, the potential is 0 again. So and v, so you're talking about three regions, three spatial regions, segments, if you like, of the x-axis. So region 1 from minus infinity to 0. Region 2 from 0 to A is here, and region 3 from A onwards, greater than A. Okay, so if this A is fairly small, then it's quite possible that this exponential decay, there's still something left. It hasn't sort of decreased exponentially to 0. There still may be some finite amount here. So then it gets into region 3, this. Where you're back to an oscillatory motion rather than an exponential die-off, if you like. So oscillatory, exponential, die-off, oscillatory again. So that phenomenon is called tunneling, because in effect the wave here, your free wave, has gone through the barrier. Even though the energy is less than this potential barrier, it's still gone through. Now, classically, that could not happen. That's impossible, classically. But quantum mechanically, you can get this kind of phenomenon. And a bit later, well, I'll just mention in passing that this particular phenomenon is actually used in technology. Like there are special kinds of transistors, from memory, so-called tunnel diodes. Right? A special kind of electronic component that actually uses the tunneling effect as its basic principle. Okay? And also this tunneling phenomenon also occurs, it's the explanation of how alpha particles get emitted from heavy nuclei in the radioactive process. These heavy nuclei spit out alpha particles. Remember, an alpha particle is just a helium atom with the 2 electrons ripped off. Right? So it's just effectively the helium atom's nucleus. Okay? So these nuclei shoot out alpha particles, and that phenomenon, that radioactivity, that kind of radioactivity, is explained by using quantum mechanical tunneling. Right? So it has various applications. All right. So you got the general setup. Now let's start solving the STI, the Schrödinger time-independent equation. Now I've done this lots of times. Now we've got three regions now. Three what's the word? Bands? No, it's not a band. Well, just 3 regions of X. Okay. So in region 1, you've got a free wave coming in. We assume that some of the wave gets bounced back in a sense. So we'll have a B here. Now K is your wave number. We're in one dimension now, so it'll just it won't be a vector, just keep it as a scalar. So k is positive is it's just a convention, but well, let's if k is in this direction from left to right, I'll assume that's positive. Now see here you've got a minus k, so that b here, the amplitude, is of a wave that gets bounced back, that goes back from right to left, right? So and the usual superposition. So the wave function is the sum of these two amplitudes, oscillatory, with the I here. Okay, now in region 2, this is the general solution of the Schrödinger equation in region 2, where there's a potential. Now, since E is less than V0, there's a term that becomes pure imaginary. We talked about this in the previous session. So the value of that pure imaginary term, your k dashed, I think it was, is just simply I big K. So we put a k here, right? And that's the general form. Now, because this is so narrow, this term doesn't drop off to nothing. So we leave both in because that's the most general form. So in region 2, you've got this kind of wave function, sum, of this form. In region 3, let's assume that the wave goes this way. We're assuming that there's no, to start with, there's no wave coming this way, right? The wave that's coming in is coming only from the left, and therefore there's no f term here, right? This wave here is your transmitted wave, the wave that went through the barrier, so it's going this way, from left to right. Okay. Well, that's the essence of it. The rest is really just algebra. Well, a little bit of calculus and algebra. So your little k, your big K, that's all defined as in previous session. So go and look that up. It's just the same here, right? Right. Well, now I've done this sort of thing several times. The next thing to do is to start matching, at these two barriers. So at x equals 0 and x equals a, these two boundary points, if you like. So we'll be able to get. Now we've got these three equations. We will be able to get 4 equations from them using these matching conditions. Remember the wave function. Just slightly to the left of this barrier, slightly less than 0 and slightly greater than 0. The wave function psi1 has to be equal to the wave function psi2 at x equals 0. Well, you just do this in your head. I mean, just look. That'll be 1, that'll be 1. So a plus b has to equal c plus d. Right? So there's one equation already relating these constants, a, b, c, d, e. Now, a bit more complicated. If you now differentiate psi1 and psi2, let x be 0, and then the differential of this has to equal the differential of that. Well, I haven't written it here. As usual, I've asked you to do this kind of thing for homework. And we'll very probably do something like this in the problem-solving session as well. All right. So that gives you a second equation. Now here, same thing. So the slightly less than a, the wave function here, should equal the wave function in region 3 slightly greater than a. So when x is a, you put an a here, and an a here, and an a here, and these two have to be equal. All right? So that'll give you a third equation. Now the gradients also have to be equal. That's not so nice. That's not so clear there, is it? I'll make it. Yeah, there you are. And you've got the gradients the same. So, so the gradient slightly less than A for psi 2 has to equal the gradient slightly greater than A for psi 3. Okay, so differentiate that, let x equal A